Please, sir.
Okay. So this is an open loop voltage control algorithm. Okay. So the setup over here, it has this inverter model from DR8301 from TI board, and you have a PMSM Technic motor, and then the power adapter, and then the TI F28069 microcontroller target from C2000 series from TI. Okay. So we're using ATAL embed to do an open loop voltage control. Then I will show you the closed loop control. So we have only the control diagram over here. If I go into the control diagrams, it has operation variables, converter variables, and then the main motor controls. So in this we'll be having your ADC channels. Sir was talking about ADC, right? To sense the voltage, three-phase currents and voltage to measure. So up till 16 inputs you can measure it, 0 to T15, right? So those inputs are, in this case we require only 7. One is to reference my DC bus voltage, another 3 voltage like RYB or ABC, whatever it is, and then you have the current. So if you go inside, these are the channels, ADC input channels. Okay, and then you also have the Clark transform, which converts your ABC to alpha beta. From alpha beta you will convert into IDIQ. So these are all the control blocks that's available. Okay, and you also have the PWM. Sir was talking about PWM, right? Comparator, registers and all. So if we come into the PWM, see here we are using PWM4. The GPIO pin assigned is 6 and 7. You have the comparator registration, action qualifier. Sir taught you what is action qualifier. How to set up with it. We are running this motor control at 30 kHz. So when I set my time period as 1500, how do I get 1500? Board frequency is 90 MHz. 90 mega divided by 1500, you can do it. Because you have up and down mode counter here, down mode, and then if you set 1500, you get 30 kHz. So if I divide it by 2, you will get 15 kHz over here. So here, I am keeping it null because, and then you can also set up your deadbands. Sir was talking about rising edge, falling edge delay. So here is a deadband, you have an option to set up. To know about this PWM, this PWM block is enough, but you have an entire detailed document available. So you can read how the PWM can be generated. Whether you want to generate for 1 kHz, 10 kHz, 15 kHz, you should know what is the board frequency divided by the time period, you get the carrier frequency. Okay. So these are the inbuilt diagrams available for you to generate. Okay. And then these are the voltage control algorithms. So you have a path reverse, space vector modulation, everything is here. Okay. So now I'm going to do the code generation of this. So I'm just selecting this block. Okay, and just go to tools, code gen. So here is the target configuration F28069. So here shows a target family and sub target is here, and then click on code gen. Okay, I'll ignore this. View the code. So today time we have generated the code. See here, December 6th, 427 we have generated the code. You can look at the entire code for the motor control algorithm. Imagine you want to write a code for controller, it takes lots of time. You may do a human errors because model based approach, why it is important, you can know about this feature. Because if you do, the memory restriction is there, code size restriction is there, all those things can be taken care because you are using model based approach. Because you are using mathematical model, that model are converted into code. That tool is doing it. Because you are spending more time on algorithm development, rather spending more time on writing a code. Okay, once you generate the code, it's a C file, and then you have to convert, just compile this, so it will generate the .dot file. So here is the .dot file. Any error it will display, you can rectify it. Okay, then I'll just quit this model. So this is actual source model. Now I'll go to a debug model. Go to Windows. I'll just open a debug file. So I'm just loading the .dot file over here. See here, now we generate 16.428. We generate a .dot file. I'm loading that file. Okay, and then I'll just switch off the converter. So this is a frequency reference. ID IQ is here. Okay, I'm just running the model. Just ignore it. I'll open the debug file. Okay. So now I'll just run the file. Now I was running. Just close it. I just showing the closed loop itself because of the time has come here. Here. So now, sorry about that. Okay. So previously I showed open loop voltage control, but I'm just showing you the current loop control. So here you are keeping a speed reference 510. So you can just monitor your 510 reference speed. So it increases like a speedometer. So you can vary your speed here, C300. So you can just see the speed here, reference speed. This is a closed loop control. I have an encoder cable here. So now I can increase my speed like a throttle. See, speed is increasing. This is the actual closed loop control. If I want to run this as an open loop, see here, I'm running this at the rated speed. So which is running at 3000 RPM. See, it's been volts. See here. So this is running at rated speed. So now when I want to do a closed loop control, so I just make the speed loop on. See now, it is running for as per the rated speed. So whatever I kept 600, it will come to 600. So I just close this. See now, speed is working as per the closed loop system. Here, controlling and increasing it. This is actual speed control. So this is a closed loop system. Which I previously open loop I just want to test it. Okay, but just for time, I'm just showing the closed loop system. So which has. So you have an IDIQ, this is a KPKA value, so you have a speed reference like a throttle, you give it, and then you can definitely have a control like whether you want to speed loop or closed loop, you can just give it. So I'm running at rated speed here. So 3000 RPM you're getting all the flags, what is the reference voltage, everything you're getting. If you want to make it closed loop, you can switch on. And this is actual, what I'm trying to show is a control algorithm, how you can implement on the microcontroller. So we have all the diagrams, tutorials are available, so you can go through. So it has an inbuilt diagram available here. Go to, just pause this, and stop here. Interactively you can just see the currents and voltages. So here, if I right click, remove XY plot. Here, see here. Now you can just see the currents, and then you can just see between the currents and voltages. So how clear it is, the two reference currents. So this is how you can spin any kind of motors, whatever I showed in the diagram, right? Whether it's an uphill motor or 1 kilowatt, 3 kilowatt, these motors you can spin it. So these are the control diagrams available, and you are programming this to a real time. This is a JTAG connectivity which is programming your microcontroller. This is your inverters and this is a controller card. So why we are using embedded to deploy our control algorithm. So we use ADCs, PWMs, SPI, all these peripherals we use for motor control applications. Just want to show you one setup, that's what does it. Okay. So probably if I have time I can deep dive, but time question I'll just immediately set up a model and I'm showing it. Okay. When I show the closed loop system, so probably you can just tell them the importance. Encoder cable, then I just show you.